Okay, so geometric distribution. We have two major formulas here. Here's our probability of successes after a waiting time of X number of failures. In other words, what's the probability of finally hitting success after 3 failures? And then in the 4th try, we hit success. And this is how we would calculate something like this, at least the probability of that event. P stands for probability of success, Q stands for probability of failure. And then our E at X here is our expectation. So our expected wait time is considered. And that would be probability of failure divided by probability of success. So they've given us a question, let's say, they said in the question that your probability is 0.2. P is equal to 0.2. In other words, a 1 in 5 chance of something happening. Okay, so your success rate is 1 in 5. Okay, and I'm just going to show you how 1 divided by 5, in case you're not sure where we got that number, is 0.2. Okay, so let's say you're, I'm not sure, rolling a 5-sided die for some reason, and you're trying to roll a 1 on a 5-sided die. Okay, this one has 5 sides, we'll say. The probability of success is 0.2. They want us to calculate the probabilities over the course of 6 trials. Okay, so what we're going to do is we're going to organize this. We're going to set it up kind of like a T-chart, and what we're going to do is going to calculate our probabilities. In our first one, this will be number of failures. Okay, I'll move that over a little, number of failures. And then this is probability of success. So you're wondering, well, how do I go about this? Well, we know our probability of success formula is P at X is equal to Q to the power of X times P, right? Well, number of failures. Our number of failures, let's say that you are successful on your first try. So in other words, there are 0 failures. Well, that means our X value is now 0. So our probability of 0 failures is equal to, and we should calculate this actually, Q is failures, right? So if success is 1 in 5, we take 1, subtract 1 in 5, 1 representing 100%, and that is going to give us our probability of failure, which is 4 out of 5, right? Or what is that as a decimal?
0.8.
Yeah, 0.8. That's going to be our failure rate. Okay, so probability of 0, well, that's going to be 0.8, which is 4 and 5, to the power of 0 times 0.2. Okay, well, what's that going to equal in the end? Do you know? 0.8 to the power of 0
is 1
times 0.2.
0.2.
So your probability of being successful on your very first try with no failures is what?
0.2.
0.2. Makes sense, right? You have a 1 in 5 chance of getting that 1 you were trying to roll on that 5-sided die, let's say. Well, let's say they want you to calculate it with 1 failure. Well, same idea. Our probability of 1 failure gives us 0.8 power of 1 times 0.2. This will be a little different in this case. In this case, we're going to get 0.8 times 0.2, 0.16. 0.16. So the probability of having 1 failure and then a success is 0.16. Okay? So we're going to go through all 6 trials when we go through this quickly. Okay? And we're just going to see how this formula works out. So 2, 3, 4, 5. They wanted to calculate it for 6 trials. So probability of 2 failures first gives us 0.8 to the power of 2. Do you have a calculator with you?
Yeah.
I want to calculate this as we go through. I'll write them out. 3 failures. So what's our probability of 2 failures?
0.128.
0.128. Okay. Of 3 failures?
0.102.
102. Of 4 failures?
0.081.
0.081. And finally, of probability 5 failures. Sorry, I did forget one other one. And then a success.
0.06.
And then finally, what's the probability of no successes. So in order to have no successes, what are we getting?
No. All of them are gonna fail.
Yes, all of them are going to fail, which means we're going to end up with, that our probability of 6 failures, or in other words, that would be the probability of having this 6 times. There would be no success at the end. In all of these occurrences, our probability of success is multiplied at the end, right? But if we're having 6 straight failures, we're not having a success. So that probability is a little different. We don't actually include the success at the end. There's no success at this one.
So could that work for 0 failures as well? Because it came up.
Yeah, we have no failures in that one, which is essentially 0.02, right? And that's exactly what we calculated it to be. Okay, so those are probability. Now let's also talk about our expected wait time. Okay, well our expected wait time, in other words, the until we get a success, our E at x was what? It's Q over P, right? Which is 0.8 over 0.2. What's that going to give us? Divide 4. So in other words, remember we said you had a 1 in 5 chance. It says your expected wait time is 4. Remember we're talking about a 5-sided die, so let's say it was 4 rolls. Okay, so our expected wait time until we got a success would be 4 rolls. Makes sense. We have our 4 failures, and then finally on our 5th one, we get our correct answer. I just wanted to check something here. Okay, so those are all of our probabilities. Now, another way we calculate our expected wait time is we actually take all of these probabilities we had before. Okay?
Add them up.
Yeah, but we also have to multiply their values. Okay, so I'm going to give you another equation that's a little more complex. Our expected wait time is also known as the sum of x when it equals 0 to infinity. Well, in this case we did 6 trials, right? And it's x multiplied by all of those probabilities. Okay, so I actually don't need this bracket here. So it's x times our probabilities. And what that means is when we're adding them all up, is we're going to sum, we have in our case, how many rolls did we have? Yeah, 1, 2, 3, 4, 5, 6. Those were 6 rolls. So that was with 5 failures. We didn't, technically this 6 doesn't come into play for this one. Okay, I just wanted to put that in there. Let's say we had no failure, no successes. Okay, so we take these values, and what we're going to do is we actually multiply them by the number of terms we're in. So let me just